present to you a project titled ProTag, Prosodic Tagging Engine for Dynamic Text. This was a research project done by myself and Mr. Elder Marks. Now, don't let the fancy words intimidate you. It's just fancy words with a simple concept behind it, and I'll show you that. Right. A brief overview of what we're going to cover: the concept, which is basically the motivation behind the research, the specific problem that we're targeting. Our solution, know that will include assumptions because it's not a perfect implementation. There are assumptions when designing systems. The question that was answered and the hypotheses that were tested in the research, evaluation, finally remarks, and acknowledgements. Now getting into the concept. We'll start with reading. We all spend a lot of time reading every day. From the time we start school, the amount of information we take in through reading increases. Right? And because of this, there's always been a desire for faster reading. With faster reading, students could be better prepared for classes. Business managers could spend less time reading emails and managing the business. With the emergence of electronic text, several techniques were developed to aid people in reading faster. One such technique is dynamic text presentation. This is basically a technique that uses a temporal display of information to aid in raising reading rates. When I say temporal, I mean with respect to time. Right? The information shown in a particular space changes with relevance to time. And one such implementation of dynamic text presentation is rapid serial visual presentation, of which I will show you an example now. Note I said the data seen in front of you changes with relevance to time. Right? If you look at the reading rate here, it's about 300 words per minute, and I'm sure some of you, if not all of you, could read and understand. Our normal reading rate is around 200 or 205 words per minute, and that was 300 words. Right. So based on this technique and RSVP, a tool was developed called PEDText Reader. This was done by Marks, Keeling Anderson and Trimble at Howard University in 2009. It's basically a fusion of DTP, dynamic text presentation, as we just saw, and prosody, speech prosody. What is prosody? Prosody is the rhythm and intonation in speech. To better understand it, think of a voice that lacks prosody, like the classic robot voice that you normally presented with, that flat monotone voice without any color to it. That's an example of voice that lacks prosody. Right? Now, the PEDText Reader was based on certain theories that were explored by previous researchers. One such theory is the implicit prosody hypothesis, which states that when someone is reading text, you automatically project some form of prosody onto the text. If you're reading in your mind, it's like you're reading out aloud in your mind, right? With some voice to it. Another is prosody and syntactic ambiguity resolution. Syntactic ambiguity basically means that with a given sentence, there could be more than one way of interpreting that sentence, right? That's ambiguity, and prosody would normally aid in resolving these ambiguities. Because based on the tone of the voice, emphasis on certain words, you could tell the context that a word is being used in, and this would help you to correctly interpret what's being said. Now, the utility, the PEDText Reader, is made up of something called a composer engine and a reading interface. This is the model that's employed by read it, it's not really clear, but the important parts. The second stage here, it basically is the content-based indication of prosody. Right, this is the part that accepts text as input, parses it, and gets it to a form in which prosody is reflected in. And then it goes on to the user interface, which presents the text to the user to help them to read faster. Now, we have demonstration. This is what the composer engine would basically look like. You see user putting text into there. And it uses a manual method, right? They put some text, and as they read, they tap their finger on the keyboard, a particular button on the keyboard, and this will generate word durations in milliseconds, right? And using this, the system is able to extrapolate some form of rhythm that will be projected onto the text. Right? And the user interface, this is what it will look like when the user starts to read. As you can see, they can adjust the amount of words per minute that they're reading at. And they can also rewind. And that's what the interface looks like. So this was PEDText developed at Howard University, which the concept behind this was that with the prosody aiding in syntactic ambiguity, as the reading rate increases, users would still be able to maintain some level of comprehension. Because previous research had shown that as the reading rate goes up, comprehension drops. Right? So even though the research did not prove that it actually keeps the rate of comprehension up, there were positive influences on the reading rate, comprehension rate, sorry. So it is a worthy research continuing. Right? Which brings us to the problem. The model I just showed you, right, is basically a model for the content-based indication of prosody. Problem, the ideal model should be scalable and accurate. Scalable in terms of the amount of information it's able to process at any given time. Accurate in that it should be as close to human speech as possible. Right? The current model, that was PEDText that we just saw, is not scalable because it depends on human input to gather the information. And obviously humans are limited in the amount of information they can process over a given time. You cannot expect someone to sit down and tap through an entire book with 1,000 pages just to get this prosodic information. Right? And it's also prone to inaccuracies because as a person reads, they're supposed to tap to show the rhythm of the text, but there would be some delay in the time it takes to click on a button on the keyboard. Right? The consequences of the shortcomings, the previous model I just showed you, it's impractical for large data sets, and there could be misrepresentation of rhythm and emphasis when the text is presented to the user. The solution we came up with, the corpus mining approach. Basically, prosodic information, instead of being gathered through human input, will be extracted from a prosody-annotated corpus of spoken language. What's a corpus? It's a collection of texts or writings on a particular topic or within a particular paradigm. The candidate corpus that was selected is one called ProPOSEC that was developed at the University of Bolton by Brierley and Atwell 2010. Now, it's not a perfect solution, as I should know. The scalability of this solution lies in the assumption that the algorithm used to implement it is efficient, meaning that there's a programmer that will code this system. If its methods are not efficient, the system will not be efficient. Accuracy. This lies in the assumption that the corpus, ProTag, is truly reflective of spoken language. If it's not reflective of actual spoken language, then the text will not be able to mimic human speech accurately. Now the revised model, just so that you know, we're not proposing to do away with the entire model that was developed by Marx et al. We're just replacing the second part that depended on human input with the proposed corpus mind. Right? Now the research question that we're answering is, can the implicit and accurate projection of prosody onto plain electronic text be accomplished synthetically? Right? This is without human input. The first hypothesis that we'll be testing is the accuracy of prosody projected onto e-text in the composer engine approach is not significantly different from that in human speech. We're basically testing here to see if the PEDText reader is comparable to human speech, if they can be on par with each other in terms of accuracy. Noting that human speech is the model for accuracy in this case. The second hypothesis, the accuracy of prosody projected onto e-text in the corpus mining approach is not significantly different from that in human speech. In this hypothesis, we basically do the same thing as we did for the first one, but testing our solution against human speech this time around. And the third one is to see which method was actually more accurate when you compare both of them to human speech. Evaluation, design of the experiment. We use a speech analyzer to get word durations from raw speech signals. You basically take an audio file, you load it into a speech analyzer, and based on the sound waves, you could get where words break and so on, and from that you can get the word durations in milliseconds. And then you use the composer engine and the solution respectively to get their word durations, and you compare the results to draw conclusions. Now the first hypothesis, which is testing to see if the PEDText reader was comparable to human speech. This was the data obtained. We have mean duration for word. We performed statistical tests. Notice how should this data be interpreted? We have an alpha value here, and basically what happens is if the p-value is below the alpha value selected, you can say that the difference between the two is too great to actually say that they are comparable, right? Now in this case, it's higher than the alpha value, so we fail to reject this hypothesis. Notice I say fail to reject and not accept, because in the scientific field they say you can never accept something. To accept it is an assumption of ignorance, right? So you can't assume that it's true just because you couldn't disprove. So we fail to reject this particular hypothesis. Right? The second one, the accuracy of prosody projected onto e-text in the corpus mining approach, which is a solution, is not significantly different from that in human speech. Again, we get a value that's higher than our alpha value, and we also fail to reject this one, which means that both methods are comparable to human speech, but in the third hypothesis, which one is more accurate? Looking back at the data, the PEDText reader, which is the original research, if you look at the mean duration and also the probability that this will be truly reflective of human speech, it's much closer to human speech than in the the corpus mining approach, which was our solution. So the hypothesis stating that our solution is better than the original research implementation was rejected. Meaning our solution was not better, more accurate than the original research. Now given these results, it didn't work out as we expected, but there's still potential in this, in that our solution is more scalable, and with further refinement, it could be made more accurate than the manual method of finger tapping on a keyboard to generate rhythm, etc. Now, the limitations of the system that was developed. There's no contextual awareness built into the system, meaning that it would take one word using different contexts and interpret it the same way. Right? So basically, no matter what way you use a word, the system will always reflect the same emphasis or tone for that word. Right? And that was the limitation of the system. Future work would be to incorporate machine learning so that the system would be able to improve its accuracy without human input. You would just expose the system to data, whether it be locally on the system or on the web, and it would try to gather information from this and develop its accuracy. And for the development of this research could spawn a new generation of readers. Acknowledgements, my family of course, for supporting me through my time at the University of Ghana. My mother is seated right here. Right. My advisor, Mr. Elton Mark, for all the insights I was given during the research project. Now, two men in particular. They were not directly involved in this research, but the amount of guidance and insight they've given me throughout my time at UG enabled me to undertake this research with minimal supervision from my advisor. So I thank them for all that. And finally, the doctors that made their work available to me, the corpus that we used to implement the system, Ms. Claire Riley and Dr. Eric Atwell from the University of Bolton. Last but not least, free and open source software developers. This presentation and all research was implemented using free software.